All right, so in today's lecture, we're going to sort of look at what happens in a case that's sort of similar to this one here. So this is the case where we have what are known as defective eigenvalues. Okay, so let's just sort of go ahead and solve this, like we were doing in the last lectures, using the eigenvalue method rather. So we're going to have 4 minus lambda, 1, 0, 4 minus lambda. Take the determinant to get the characteristic polynomial. So we get our characteristic polynomial of just lambda minus 4 squared. Okay. Well, we got one eigenvalue of 4. A lot of times we got 2. This time we got 1. Nothing is necessarily wrong yet, but let's continue. So we'll go ahead and try to find our eigenvector. So we set this up and we get the system of equations b equals 0, and for the second equation we get 0 equals 0. Okay, so really all we can conclude from this is that b equals 0. It's sort of weird that there's no a here, but it's not actually a problem. We would just say that our eigenvalue is, let's say, c1 times 1, 0, or 1, 0. So it sort of might be a little confusing what to do next. You might maybe just think that we just say, okay, x prime is c1 e to the 4t times 1, 0. But, I hope to some of you might be saying, no, that doesn't really feel quite right. So let's ignore this answer for now. And if we note, this system of equations is actually pretty simple. So let's just try to write it as a normal system of equations and see if we can solve it in another way. So x prime equals 4x plus y, and y prime equals 0x plus 4y. All right, so from this y prime equals 4y, we know right away, okay, y equals c1 e to the 4t. Very straightforward. Plugging that in, x prime, equals 4x plus c1 e to the 4t. We could now go ahead and solve this, right? X prime minus 4x equals c1 e to the 4t. Use our integrating factor of e to the negative 4t, ... But I'm just going to tell you that at the end of that process, which I trust you guys could finish now by yourself, we would get that x is equal to c1 t e to the 4t plus c2 e to the 4t. All right, so we have sort of our solution. Let's try to write it back in sort of this vector form. So let's see, for my x coefficient, so I'll do c1 first. For my x coefficient, I'm going to have e to the 4t there, but then I'm going to have t, and then just a 1. For my second term with a C2, it's just going to be C2 e to the 4t, and then 0, 1. All right. So it turns out sort of we were right to, not trust that we were done here at this step when we only got one eigenvalue. I mean, as we can see, we just solved it and found that we were missing, half of it, let's say. But there's sort of a more general reason why we should be wary of stuff like that. I'm just going to touch briefly on what solutions look like to these kinds of equations in general. So we have sort of the following result. So given some matrix, and remember that we can really treat this as a matrix of functions, presumably, let's say, continuous functions. So if we have this matrix of functions and we have a linear system like this, so if you have two solutions, so if x1 and x2 are solutions to the above equation, then so is some constant c1 x1t plus some constant 2 x2t. And moreover, if x1 and x2 are linearly independent, and what linear independence means in this context, I will say a little bit more in just a second, then the general solution to, let's call this, equation 1. Is precisely xt equals c1 x1t plus c2 x2t. All right, so this lets us know in general, right, that we should always expect two constants, and it should look like this. Let me say a little bit more about what linear independence means in this context. So we'll say x1 of t and x2 of t are linearly independent if there is some t0 so that if I try to solve this in terms of so I've plugged in my t0, call this equation 2. And R and S here, it's important, are not matrices, but just scalars. So no matter what x1 and x2 are, right, I can always find one solution, which is the solution where I just multiply both by 0 and add them up. But what's important is that that is the only solution. So this is what linear independence means in this context, and I will do 2 brief examples. So rather, I'll do an example and a non-example. All right. So first, we should note that e to the t times 1, 2, and e to the t times 2, 4 are not linearly independent. Right, because I can sort of see if I do 2 times the first one minus the second one, right, I'm going to get 0. So that one's pretty straightforward. A slightly less straightforward one is I can replace this e to the t on the second one with, say, 3e to the t, or really any other function. Since, let's say I plug in t equals t0. Well, then I want to solve r e to the t0 plus s e to the 3t0 and if I sort of pull out a 2, it's a little bit even easier to see. Right, so I could set, r equal to, let's say, 2e to the 2t0. And I could just set s equals -1. Right, and if I bring this all in, -2e to the 3t0, -4e to the 3t0, then yeah, I'm going to get 0, 0. And then sort of lastly, so e to the t times 1, 2, and e to the t times 0, 1 are linearly independent. And the reason for this is, I mean, if I try to solve, right, I can pull out e to the t, and let's say, at t equals 0, right? You can do it at any value at t equals 0. Let's say we have a 1, 2 plus b 0, 1 equals 0, 0. If we convert that to its system, right, it says A plus 0 times B equals 0, and 2A plus B equals 0. And, from this, A equals 0, and then using that for the second one, we see, okay, B also equals 0. So A equals 0, B equals 0. So that's the only solution, which means they're linearly independent. Okay, so sort of the key thing to take away is it doesn't really, right, before when we talked about linearly independence, we sort of used the Wronskian, and it really depended on sort of what the function was. Here, that's not as important. It's not so much what this function in front of everything is, it really has more to do with the vectors themselves. Okay. All right, so we now know sort of a little bit more of, say, what to expect. So let's look at another example where we have this phenomenon and see if we can figure out what the sort of general solution is going to look like in this sort of case where we only have one eigenvector. So we want to find the general solution to the above equation. So let's go ahead first and just verify that, yeah, we do only end up with one eigenvector in this case. Remember, I'm doing the thing where I cancel out the negatives. All right, so we have lambda squared plus 6 lambda plus 9. So we can factor that as lambda plus 3 squared equals 0. And so what we end up with is lambda equals -3. That is our only eigenvector. So we can go ahead now and try to solve for our eigenvalues. And what we'll get is A plus B equals 0 up top, and negative A minus B equals 0 down below. So we can sort of see that, okay, A is just equal to negative B, so in general our eigenvalue looks like C1, 1, -1. Okay, so again we're sort of in the same case. We have an eigenvector, right? From this we can sort of go ahead and say that, e to the -3t C1, 1, -1 is a solution, or is sort of a collection of solutions, but it does not have the whole picture. So how can we maybe go about solving this? Well, what we're sort of going to be looking for is sort of, remember, we're going to use this thing where we want to find ax plus by, where if we take the derivative of that, we get -3 times what we started with. Oops. And it turns out that the way we can find this is we sort of do the same computation up here with the same matrix. except we're solving for this thing where a and b is a long vector as opposed to a tall one. But we'll get sort of something pretty easy. So 1, -1, 1, -1, AB equals 0, 0. And what we can see is that, there's lots of options, but we can just take A equals 1 and B also equals 1. All right, so this tells us, right, that x plus y prime equals -3 times x plus y. And we could go ahead and verify that if we really wanted to. I'm not going to do that here, right? But we have this system of equations as well. X prime equals -2x plus y. Y prime equals -x minus 4y. That just comes from converting our original matrix system to the sort of more expanded form. Right, so that's where those coefficients are coming from. And yeah, if you add these together, you see you get -3 for the coefficients of both x and y, so that sort of verifies it right there. All right, so continuing, right, this lets us know that x plus y is c1 e to the -3t. And so we can just say, okay, x equals c1 e to the -3t minus y. We could plug that in, say, to the second one, so y prime equals -x, which is c1 e to the -3t minus y. From here, we could go on and solve this. We would get that y equals -c1t e to the -3t plus c2 e to the -3t, and x equals, if I use this equation in there, let's see, we would get that x equals lost my thing. Oh, 2. No. Yeah, x equals just c1 e to the -3t plus c1t e to the -3t minus c2 e to the -3t. Writing it back in vector form, we get something that looks like this. So c1 e to the -3t, 1 plus t, -t, plus c2 e to the -3t, -1, 1. I'm going to write this in just a slightly different form to sort of show more of the structure that's going on here. And I'm also going to use the fact that I can rescale C2. So just multiply it by -1 to get this. Okay. So there's sort of a couple things that I think we should take note of here. So we'll note that this, so 1, -1, that was our original eigenvalue. Or rather, our eigenvector. It's still not clear where this thing comes from. And if we go back up to the other example that we solved, back, we could rewrite this, right? Let's rewrite this guy as a, oh, I actually wrote down the wrong answer here now that I look at it again. This should be 1, 0. So if we rewrite this guy, C1 e to the 4t, we can also write this as a 0, 1 plus t 1, 0. And then if I have the right answer, I can see again, I get 1, 0. So again, sort of I have my eigenvector here, which is present, and we still just sort of don't know where this other thing comes from. Okay, but we can sort of see the pattern, so maybe we can try to figure out what that other guy comes from. So let's say we have a matrix A of constant coefficients. And there's only one eigenvector up to rescaling. So in this case, we say lambda is a defective eigenvalue. All right, and now let's look at, so let's say in this case, we're studying this equation. So we have a defective eigenvalue lambda, and with eigenvector I'll just call it V1. Okay, so we know, right, x equals C1 e to the lambda t. V1 is a solution, but not the general solution. And based sort of on these examples, right, it seemed that we always picked up a t, and that t was always also associated to the eigenvector. So let's look. That looks like this. So x of t equals C2 e to the lambda t times V2 plus t times V1. Okay. expand this once more, just because we're going to take a derivative and it'll make it a little bit easier. So what we want to just set up is, the system. So x prime t equals a times x. So if this is our x, right, what is x prime? Well, x prime is going to be c2. And actually, let's just get rid of c2 because we know we can set it equal to, say, 1. So x prime then is going to be lambda e to the lambda t v2. And then plus, well, we take the derivative of the t first. And then we take the derivative of e to the lambda t. Okay, so that's our left-hand side. On to our right-hand side, right, we're going to have A, so which is our matrix, applied to just this whole thing. Every term has a sort of lambda in it, so let's just divide, or e to the lambda t, so let's just get rid of those. So simplifying on this side, we have lambda v2 plus 1 plus lambda t v1. And over here, we have av plus t, and normally I can't commute matrices, but t is just a scalar, so I can't commute it with that. And then moreover, remember that by assumption, I know what happens if I multiply a with v1. I get lambda times v1. So a v2 plus t, plus lambda t rather, v1. And now I can cancel some things. So I can cancel that term with that term. And now I'll get my equation that I want. So a times v2 equals lambda of v2 plus v1. All right, so in this case, we actually have a name for things like this. So if v1 is an eigenvalue or an eigenvector of A with eigenvalue lambda, and V2 satisfies this equation, we say V2 is a generalized eigenvector, or a generalized eigenvector. And then so we see that our solution is going to look like this, right? So in general, what we have is, yeah, C1, our eigenvector V1, I'm sorry, our e to the lambda t times our eigenvector V1 plus C2 e to the lambda t times V2, our generalized eigenvector, plus t V1. So this is our form of our solution if we have a defective eigenvalue. All right. So I'm going to do a few examples, and So here we're going to go ahead, right, find our characteristic polynomial. And we can see it is just going to be lambda minus 5 squared minus 1 times 0. And so we get, right, our only eigenvalue is going to be 5. So we set up our equation, right? We're going to get 0 times a plus b equals 0, and well, 0 times a plus 0 times b equals 0. So again, we'll get that b equals 0, 0 equals 0, and again, the sort of thing to conclude here is, oh, okay, that means that a is whatever it wants to be, but b has to be 0. So say, something like c1 times 1, 0. Okay. What we want to do next is find our generalized eigenvalue. And so, this sort of the explanatory bit. So what we want to have happen is we multiply this matrix to some vector v, and what we end up with is our eigenvalue plus, so 5 times v plus this thing here. So we have to choose a specific C1 value, so of course we'll just do 1, make it easy. And so we get something like this. Now you could solve this equation, but again, we're going to sort of do a shortcut because it's also going to let us reuse this matrix. So if we just move it over to the other side and write this 5 as a 5 times what's known as the identity matrix, right, then what we end up with is sort of this. So 5 minus 5, 1, 0, 5 minus 5, and then times, I'm just going to reuse AB. The only difference is now we're setting it equal to 1, 0. And now what we're going to get is actually B equals 1 and A equals, and 0 equals 0. So we could again assign A to be any value we want, but B has to be 0. And so we could get our generalized eigenvector of 0, 1. Okay, so we have all our pieces. Now we're just going to write down the solution. So x of t is equal to c1 times e to the 5t, and then we'll do the easy case where we just have that eigenvector 1, 0. Okay, plus c2 e to the 5t, and then we want to do our generalized eigenvector 0, 1 plus t 1, 0. Okay, so that's our final answer. So one thing I'll note, and I'll point this out again sort of later. So this, in this case, it could be replaced with, we could have any vector of the form now let's say A1. And really where this A comes from, I mean, it's pretty clear from solving the equation, but in general, this thing, you can't just scale it and get the answer the same like the eigenvector. What it actually, the different answers differ by is every answer can be written as like one answer plus some scalar multiple of our eigenvalue or our eigenvector. So note the eigenvalue or the eigenvector, it's pretty clear to say if you're like comparing answers with your neighbor, pretty easy to check that, you know, even if your answers differ, oh, they're both right because they differ up to scalar. Right, so I could have made this a -1 or a 2 or something like that. The problem here is, so this is going to depend, first of all, on the eigenvector you choose here. It's also going to depend on, it could also vary by some sum of the eigenvector. So your answers to this can vary quite differently from someone else, even though both answers are right. And that's definitely going to happen if you guys have differing eigenvectors to begin with. Okay. So I'll do 2 more examples. This first one is pretty quick. So it's important to note that just because your characteristic polynomial has only one root, meaning you only have one eigenvector, that doesn't mean that you're necessarily gonna be of that form. So we'll look at sort of a real simple example, which is this. So, you know, get our characteristic polynomial. It's clear then that our only eigenvalue is 3. But if we set this up, right, we're actually in a bit of a weird case. You might notice we've already sort of we solved an equation like this at the beginning. It's what's known as an uncoupled equation. So we just get 0 times A plus 0 times B equals 0, and the same for the second one. So really we just end up with sort of the trivial equation 0 equals 0. So in fact, we sort of saw that, you know, this doesn't really seem to pop out an eigenvector, but really what this says is actually any eigenvector you choose, or any vector you choose, will be an eigenvector. So one way of writing that is we have eigenvectors something times 1, 0, right, and something else times 0, 1. And so in this case, it's very easy to write down the answer. It's our eigenvector 3t times c1, 1, 0 plus c2, 0, 1. So the key thing here is just because you only have one root doesn't necessarily mean you have a defective eigenvector. You could have a situation like this on your hands. Though I'll say that for 2 by 2 matrices, it means in fact you have to have something that looks exactly like this. You know, some entry on the diagonal and everything else is 0. All right, I will do one more before I give you a couple to work on. So let's solve x prime of t, -23, -9, 49, and 19. All right, so we find our characteristic equation. Okay, 23 plus negative 19 is going to be positive 4. And then 23 times 19, you'll probably have to use a calculator for, but you should get a negative 437. Over here, well, let's see, 9 times 50 is 450, minus 9 is 441, so plus 441. And of course, this factors as lambda plus 2 squared. And so we see that lambda equals negative 2. All right. So we have negative 23 minus negative 2, negative 9, 49, and 19 minus negative 2. Just simplify that first. We get negative 21, negative 9, 49, and 21. Okay. We're setting that equal to 0. And, we can go through, hopefully you guys are used to this part, and we should get, our eigenvectors look like negative 3 and 7 times some constant. Okay, so that part's the same as before, but now, we have a defective eigenvalue, so we need to find our generalized eigenvalue. So what we do is we take this same equation, right, and we just set it equal to the answer we just got. So that was negative 3 and 7. This one you do kind of want to avoid using the C1. It's just going to make things more complicated. Okay, so now we need to find any solution for this. So negative 21a minus 9b equals negative 3, and 49a plus 21b equals 7. So if we go ahead and divide the top one by a negative 3, we get 7a plus 3b equals 1. And if we go ahead and take the bottom equation and divide by 7, right, 7 squared is 49, so 7, 21 divided by 7 is 3. All right, so the same thing works as before for double checking your work with eigenvalues and generalized eigenvalues. You should get essentially the same equation at the end. We just need any solution. I like mine to, sort of be as nice as possible, so let's do a equals 1 and b equals negative 2. All right, so now we'll just go ahead and write down our answer. Oops. Okay, so e to the negative 2, negative 3, 7, plus c2 e to the negative 2t. Then we have our generalized eigenvalue, or eigenvector, plus t times our eigenvector. And that's our answer. One thing to note here, so normally you can rescale your eigenvector. The only thing to be careful of here, note where this C2 is. So we could rescale this, in fact, to even be different from something here. But if I rescale this one, I also have to rescale my generalized eigenvector as well. Okay. So I want you to find the general solution to the following two systems. All right, so give those a shot. And yeah, I'll go over the answers now. So just sort of give you a brief outline of the points you should be hitting. Okay, so first of all, you should get that your characteristic polynomial is lambda squared minus 12 lambda plus 36 for the first one. This says that lambda minus 6 squared equals 0. So of course lambda equals 6. You go ahead and solve for your first eigenvector. Should have something like 15, 9, right? 25, negative 15. Oh, negative 25, negative 15 times AB equals 0. And you should get something at least up to scalar that looks like negative 3, 5. Now for your generalized, you do 15, 9, negative 25, negative 15 times AB, except now you set it to equal to whatever you got in the first part. Your generalized eigenvector, again, many different possibilities, but I got 1, negative 2. The only thing to check is, does this satisfy this equation? So 15 times 1 minus 2 times 19, that's 15 minus 18, negative 3. Negative 25 plus 30 gives us 5, so I know that my answer is sort of correct. Okay, and now you just write down your final answer. Right? So hopefully that was, straightforward. Numbers were kind of difficult, but it's pretty straightforward. For this one, I'm just going to jump to the answer. Characteristic polynomial is lambda squared minus 4 lambda plus 4. But we have two eigenvectors, so e to the 2t c1 times 1, 0 plus c2 times 0, 1. All right, and I'll end it